I want to talk today a little bit about real-world use case of CoreOS and etcd. So first, a little bit about me. My name is Kukulinski. I'm the co-founder of Yodlr. It's a communication platform that runs entirely in your browser. I also run a Node.js meetup in the South Bay, so if you want to talk Node.js, I'd love to talk. Huge Docker fan, and while I think Rob is definitely my Batman on IRC in helping out with problems, I hang out on Freenode on the CoreOS channel as Ross K, so I'm always happy to help do my best to answer any questions you might have. Yeah, all right, so today, I want to talk a little bit about our story at Yodlr and why we switched to Docker and CoreOS. I'm going to talk a little bit about specifically how we're using etcd, and then I have a couple of plugs that I want to do for a couple of projects that I want you to keep an eye out for. So first of all, Yodlr. Yodlr is a browser-based communication platform. We originally built this as an internal tool for our company. We had tried using Skype and Google Hangouts, and we tried Cisco, and we tried a bunch of things. And as a communication system, our parent company built communication systems for flight simulators and military training. And we ultimately decided, you know what, let's just build our own little internal tool. We'll use it for my team that's based here in California and the parent company that's based in DC. And so we built our own little tool based on Node.js. It was really just a prototype using WebSockets, some WebRTC stuff, and it was great. Until the internal tool was no longer internal. We started using Yodlr as a sales platform to sell our parent company's flight simulation products to some of our customers. And we had a couple of customers that were more excited about Yodlr than they were about our communication products. So we started, and they wanted to know, hey, can we use this Yodlr thing? So we said, sure. So we started with the private beta, and we've started scaling up the number of users. And this little side project suddenly became the side project no more. And we really realized that we needed, in order to scale, in order to handle this additional customer load, that we really needed to rethink our entire infrastructure, sort of start over from scratch. So some of the goals that we were keeping in mind, number one, we wanted to reduce our application complexity. We had built this one monolithic Node.js app because it was quick and easy. But as we were growing this team that was working on the Yodlr platform, we needed to split things up, and each individual developer needed to know lots and lots of different pieces of unrelated things just to sort of make and do development on the app. We also wanted to do a lot of A/B testing of our applications. So we wanted to run, if we improved the performance, we thought we improved the performance of something, run both instances of the application, one old version and one new version, run them side by side in production, and route certain amounts of traffic to each one. Developers should be able to have the same environment when they're running their application. It's the same in dev, test, staging, and eventually production. Obviously scalable, because this is going to be massively successful. Fault tolerant, because things do go wrong. And we're a small team, and we're not really DevOps people. We're more application builders. So we wanted to minimize the amount of time we have to be mucking with DevOps. So enter Docker. So Docker for us, some of the things that we started realizing as we were doing our research. And actually, let me back up. So who in the room is currently using Docker in some way? OK, good. And then what about CoreOS, like dev? You're playing with CoreOS? OK, who's using CoreOS in production? OK, so only a handful of hands. All right, cool. I want to pick your brains, too, on lessons learned. So some of the advantages of Docker that we recognize. So Docker containers start very, very quickly compared to a traditional virtual machine. They have a small footprint, so you can run lots of containers on a single host. One of the things that we liked was the Dockerized applications you can run anywhere. So we took our giant app and we stuck in a Docker container, and now we could run multiple versions of it all on the same host machine. The fast builds, registry, and the fact that the images can be all stacked. So these things checked off the first 3 items on our list. So then the next question is, how do you ship containers? Obviously, you can write bash scripts for everything if you really hate yourself. You could use Ansible. I love Ansible. Also Puppet and Chef. But that ended up, we started playing with that, and we started realizing that we were going to have to write lots and lots of deployment code and nastiness. And that's when we stumbled upon CoreOS. I'm going to skip through a lot of the CoreOS benefits because I know that a lot of people are already familiar with CoreOS. The big things for us, it runs Docker containers. You can run it in any major cloud. So we happen to be a Rackspace customer. But we also run our own bare metal infrastructure in-house for dev and staging. So the fact that we can run a complete replica of our production environment on bare metal in our office is outstanding. etcd as a distributed key value store is huge, and that's something that we use throughout infrastructure, and I'm going to talk a lot more about that. And it's scalable. This picture should look familiar. I stole it from the CoreOS website and documentation. It really is. Just to be perfectly honest, we have not gone to this sort of hybrid model of having the core etcd cluster and then a whole bunch of workers. We will eventually go that way, probably when we make the switch to etcd 2.0. But for the time being, we just have one etcd cluster, and that's where we have all of our services. So that checked off all our list. Everything is there. There are still some things in this minimized time spent doing DevOps that I think are still missing from the CoreOS infrastructure, namely some tools to help with automated deployments and rolling deploys. Right now, our deployment process is still a manual fleet control, stop this service, fleet control, start this service. Luckily, we don't have too many services and we don't have hundreds of machines, but when we get to that point, we're going to need some tooling. We're keeping a very close eye on Kubernetes. But I don't think it's quite there yet. I'm hoping that later this year in 2015 that Kubernetes will finally be there. But I'm not an expert in Kubernetes. I think you should talk to some of the CoreOS folks. And if there's any Kubernetes people here, definitely you should talk to them. OK, let's talk about now the good stuff. So how does our infrastructure actually look like? So this is our current infrastructure. Wow, it's a simplified version. Basically, we have the public internet is talking to Rackspace's cloud load balancers. You could do EC2 load balancers. Let's see if I've got a pointer here. Aha, I've got a pointer. Excellent. So you could use EC2 load balancers as well. So Rackspace has this idea of a service network. The service network is shared across customers in a data center, so it's not a secure network. Do not run etcd on the service network, especially if you have secure stuff in there. We have, in this case, we've got a set of 5 CoreOS hosts, and then we are using a separate private network that we have set up in our data center, and that is specific to our machines. So only the machines in our production cluster are tied to a specific production private network. And for each environment that we have, if a developer wants to run their own cluster, they have their own private network. So on our public network for security purposes, really the only thing that we have there is SSH. If you're really security conscious, I guess you could not have any SSH there and have like a separate one machine that's unrelated to your clusters, and like that's your entry point to then access through their private network. I don't have time for that. There's the service network. We connect to the load balancers, and they connect specifically and only to internal load balancers inside of our CoreOS cluster, and I'll get to that. And then on the private network, that's where etcd and Fleet, Fleet uses etcd, and then all of our microservices, which are primarily HTTPS and UDP streams for audio, they all run over that private network. Are there any questions so far? OK. So microservices. So I'm a big fan of the Unix philosophy and also Node.js of building one thing and doing one thing well. And that's how we've built our infrastructure. So we took our giant monolithic app and we broke it up into a bunch of microservices. So for example, we have a chat service. I only have one instance of a chat service here, but because CoreOS machines will go down as they're part of their rebooting, you need to handle failover of hosts. And so for each service, we run multiple instances. So here's an example. I have an instance of audio service number 2, an instance of audio service 1. Now what happens if a customer hits our public web page and wants to view our marketing information? So that comes in through public DNS into Rackspace's cloud load balancer, and it hits one of our internal load balancers. Then from there, the load balancer proxies it to one of the marketing sites that's running on our cluster. Now here, I'm only showing 2 of those 5 nodes. We run multiple instances. We run multiple instances of each of the service across the cluster. And that really comes down to how much if you've got a 5-node cluster, if you have 1 node downtime, you're rebooting or something, or 2-node downtime, we tend to run 3 instances of each service at a minimum just to make sure that we have uptime across all 5 of our CoreOS machines. But again, this is something that we're playing with as we move to this idea of having our core etcd cluster, which is a database, and then our workers, which will run all of our microservices. So how do the Rackspace load balancers know where to send traffic? Well, we use something called service discovery, and we do it using etcd as our data store. And we wrote an open source package called rackslb config, which really we should rename it because we built it specifically for Rackspace, but the underlying library we use that talks to Rackspace's APIs is cloud agnostic. So it supports Amazon and Joint and Rackspace and DigitalOcean. So this library can be used across any cloud platform. So who here has heard of this Sidekick pattern? Okay, so a third of the hands. All right. So a couple of times in the IRC channel, people have asked questions about sidekicks and stuff, and I ended up just sort of documenting an example Redis sidekick pattern. So the examples I'm going to show are sort of shortened and squished to make them work on the slides, but please take a look at that full URL. It's a gist. Okay. So we've got Redis. Redis is a key value pair database system. Arguably, you might ask, why are you using Redis when we have etcd? That's a separate discussion. But in this case, we have some unit file. So here we have, do people know about unit files? Do I need to explain like how unit files work? Raise your hand if you don't understand unit files, and I'll do a quick, okay, there's a couple hands. So in CoreOS, if you have a service and you want to deploy it to your system, use something called Fleet, which Fleet has been mentioned. Fleet's a command line interface and a REST API behind the scenes. It talks to etcd, and it's a very rudimentary scheduler for running services on your CoreOS cluster. And CoreOS behind the scenes uses systemd to manage the running of services. And so Fleet's unit files or service files are really systemd service files with a little bit of extra magic stuck in at the bottom. There's no CoreOS magic on this, but on the next slide there was going to be some CoreOS magic. The basic idea is you define your unit, and this is sort of a description to systemd. What is this unit? What's the description? What other services does it depend on? In this case, this Redis requires Docker, because we're going to be running Redis in a Docker container. It requires the Sidekick, and the Sidekick is going to be reporting information about this Redis container. And then in the service section is the commands that are actually run by systemd to start or stop or reload your service. In this case, our simple is our exec start is doing a Docker run. We're specifying the port that we're going to bind to, or we specifically the IP address and the internal Docker port. Sometimes you'll see in CoreOS or in Docker, you can put a port right in the middle there. That sort of is an exact mapping of host port to internal IP port within your Docker container. We specifically do not hard code the host port. And the reason is we want to be able to run multiple instances of every service in our cluster. And so by not specifying, we have host IP and then not specifying a host port, Docker will automatically figure out some port to use on the host system within its bank of ports. This prevents collisions of 2 services coming up and trying to use the same exact port. So our developers can always bind to port 3000 or whatever port they want to inside their container. And then the operations side, Docker says, all right, you're going to have port 49721. Then we have Redis latest, and then Redis server is the command that's going to be run. Questions so far? OK. So what does the Sidekick need to do? So the Sidekick, again, it's going to be requires Docker. It requires etcd to be up and running. And it's going to be after Docker, after etcd. It's after app Redis, which is the original container. And it also binds to app Redis. Now, this sort of configuration seems a little weird. But what it basically means is app Redis, it requires the Sidekick. So before it starts, or at the same time as it's starting, it's going to be starting up, it's going to try to start up and this is systemd. Systemd is going to start the Sidekick. The Sidekick says, hey, I'm supposed to be after the Redis container actually comes up. So our Redis container comes up, then our Sidekick comes up right behind it. And then importantly, binds to. What binds to means is that if our Redis container goes down, our Sidekick will also be taken down. And I'm going to get to why that's important. Our service has got a little magic bash script, which I've hidden away. And then the last important piece, this is the fleet-specific information, is this machine of keyword. What this basically tells Fleet Scheduler to take this Sidekick service and make sure it puts it on the same physical host as the Redis primary container. And for the sake of simplicities, I've not put the whole bash script, and there might be some nicer ways to do it, but we are using bash, a simple bash script. But the short and sweet of it is, the service first needs to get the port that Docker has dynamically assigned to that primary Redis container. And Docker inspect -- format allows you to specify a Go template to go and find and pull out just the port. We do a health check. So not only is we make sure that the container that has Redis inside of it is running, we also want to make sure that, hey, Redis, are you running inside there? And then finally, we write the IP port data to etcd under a certain namespace. So it might be under /services/Redis. And what that allows us to do is everywhere else in our infrastructure, if you need to access Redis, you query etcd and say, hey, Redis, or hey, etcd, what is the value in /services/etcd? And it's going to give you back an IP:/port mapping, which then you can plug into your Redis CLI. Questions? Yes?
Why do you not use Docker's link feature? It seems like this kind of re-implements that.
Great question. So one of the reasons is, as far as I know, the Docker link feature does not work across physical machines. And so there's no guarantee that where Redis is running in our cluster and an app that needs to use Redis are going to be on the same physical machine. If your nodes are going to be on the same, if you know that you do an X machine of with your service and you know it's going to be on the same physical machine, you certainly can use the Docker -- link. But in our case, we wanted to have the flexibility of moving services across any of the machines. Other questions? OK. So this is all the Sidekick pattern. We apply this to our load balancers. So within our internal load balancers, we're using Nginx. You could use HA proxy, or vulkand is another one that sort of automatically does a lot of this stuff behind the scenes. In our case, what we do is each of our Nginx top-level load balancers writes their IP import information to etcd under load balancers, the name of the load balancer, and then a node number. And what RacksLB does is it will automatically monitor etcd and update our Rackspace cloud load balancers for that load balancers and add and remove nodes as these Docker containers maybe get moved around as you reboot systems. Question in the back.
If I wanted to use Nginx as my load balancer, do you know of anything that can kind of do what you're doing there, where it auto-updates the load balancer, but updating Nginx to tell it where to be routing to?
You mean, so the question is, how would you do this if you wanted to update Nginx? Yeah. And it's a great question. I'm going to get to that next. How do the internal load balancers know where to send the traffic? Well, we use the same pattern. So again, we're using service discovery with etcd and now something called Compte. And I think Kelsey mentioned this, or maybe Brandon mentioned Compte earlier in talking about etcd. So Compte is a very simple, it's open source, it's up on GitHub. It's a Go runtime that monitors etcd or console or theoretically environmental variables on your system. And it dynamically updates your config file based on a Go template. So if the etcd key for one of your upstreams changes, Compte will monitor and say, hey, this key changed. I need to update the configuration file. It can also verify that the new config that would be written is going to be correct. And then it'll write that to your system. And as I mentioned, we're using Nginx, but you could use HA proxy or any other sort of load balancer. You also can use this for other things. So if you wanted to dynamically rewrite let's say you're using RabbitMQ and you need to set up the configuration file for it for the different host machines. Then you could use Compte to dynamically rewrite your RabbitMQ configuration file based on the data that's in etcd. Does that answer your question?
Yeah, perfectly.
Excellent. And just to give you an example of what this templating looks like, it's Go templating. So here we have defined a key services Nginx/marketing. So we have an upstream, so the squiggly brackets represents the Go templating. Then the stuff that's inside here, this is Nginx configuration. So we're defining an upstream called marketing. We're saying, hey, we want to use a least connections algorithm. And then here we're iterating over services/Nginx/marketing star. So we have marketing/node1, marketing/node2, marketing/node3. Each of those values, the IP port is going to be dropped in where that period is. And there's a bunch of examples in the Compte documentation of different ways of structuring and writing out that data. Okay. So next, one of the things that we love, or I love command line tools. I'm a developer at heart, and Fleet and etcd have great command line tools. But one of the things that we quickly got frustrated with was constantly having to rerun our fleet control command to list machines or list units. So one of the things that one of my team members, Jared, did is he went off and wrote what we call Corgi, and Corgi is an open source system for monitoring your etcd and CoreOS system. It's a simple little web app. It's got machines, units, unit files, and etcd. It's the same information that you would get out of your fleet control, list machines, list units. In fact, we use fleet behind the scenes. And it's a Node.js Angular application. I know a lot of people here are like Go people. We don't know Go, so we wrote it in the thing that we know how to use. Again, we love pull requests, so it's something that we're actively working on. And if you have some ideas, definitely would love to talk to you more about that. We're using Fleet and etcd to monitor the CoreOS cluster. And as of right now, we support listing, starting, and stopping units that are already defined in the cluster, listing machines, and listing etcd keys, which we just rolled out last week. Some of the things that we're looking at adding in the coming weeks here are things like being able to upload service files, being able to start instances of templates, the types of things that make our lives easier when trying to manage CoreOS clusters. Any questions on Corgi? Cool. Definitely go check it out. I would love your feedback. It's a Docker container, and we've in the GitHub repo, which is here. We've already included service files, so you can just do fleet control start. If you check this out, fleet control start services/Corgi, and that'll automatically start it up as a global service within your CoreOS cluster. Obviously, you should not make this publicly accessible. By default, the global service just listens on port 3000 on the public IP address, because we usually use that. That's like our default service file when we're running in dev mode. In production, you should rewrite that service file to listen on a private network, only make that available through a private load balancer, which has got some sort of auth on it. It's not my fault if you leave this Corgi open and someone comes in and starts stopping services, or once we add the ability to edit etcd keys and they start changing etcd information. Not my fault. Yes?
How does it look like for starting units or creating a new unit file?
So we have not done that yet. I should have. So Jared has done the UI for that. I think I don't have any pictures with me, and I don't have a cluster I can access from here. But the basic idea is under units, if you already have defined a unit file, there will have, like, here's the list of all your templates, and then there'll be a sort of a plus expand button. And in theory, we're playing with the idea of saying, hey, we've already noticed that there's 3 instances of this service. Maybe there's a plus button and a minus button that'll automatically do that. It might also be on a per service basis. It's something we're still playing with, and we'd love feedback. So if you have some ideas on ways it could look or how you might want to use it, please, please, please talk to me or post some issues to Corgi. All right, so I'm just about done here. So a couple of shout-outs. Number one, I organize a Node Node.js meetup in the South Bay area. If you do Node.js, love to talk to you. Container Camp is coming in April in San Francisco. The call for presentations is now open. I think, I know I've submitted my talk. I don't know if I'll get in, but I'm there. And then the last thing that I want to pitch is something that Ken Perkins, who's a Rackspace developer advocate, worked on. He wrote something called CoreOS Cluster Cli. It's a little CLI tool, and hopefully we can see this. It's basically a simple CLI tool that allows you to define a cluster size and which channel, and it'll automatically bring up a CoreOS cluster in Rackspace right now, just Rackspace. But again, the same library that we're using under the hood talks to Amazon, DigitalOcean, Joyent, Rackspace. So it would not be hard to harass Ken to add support for some of those other services. So we use this when we want to stand up a dev cluster to start playing with, CoreOS CLI, bring up a bootstrap a machine, and then you're good to go. The last thing that I've got is, I mentioned this earlier, we use CoreOS on bare metal. This is actually a picture that Jared took for me earlier today. One of the questions, or one of the things that we've found in our experience in using CoreOS on bare metal is the documentation obviously still needs some TLC, but we weren't really DevOps people, so we didn't know how to set up Pixie servers or DHCP servers and how to link them all up and get the cloud config set up and how to find out which MAC address of which machine to route to, and we had to set up all this stuff. And we've set it up in a Docker container, and we're starting to play with setting up a little app that allows you to manage those cloud configs and actually run a DHCP server, the TFTP server, and a simple web server that has the cloud config file. We're trying to decide whether or not we should do a little bit more work on it. Is there anybody here that is like doing, okay, so Kelsey already wants this. Anybody else would want something like that?
Yes.
Okay, cool. Find me afterwards. I want to get some input on how you're using it and what sort of things you might be looking for and how it might work. Yeah. That's all I've got. Thank you.